Something extraordinary is happening right now, and the silence from official channels is deafening. Is really 3i Atlas took an impossible orbit? While NASA carefully constructs its public statements and academic institutions debate methodologies in sterile conference rooms, amateur astronomers across the globe have captured images that fundamentally challenge everything we've been told about 3i Atlas. These aren't ambiguous smudges or artifacts that require interpretation. These are clear, detailed photographs showing structures and behaviours that shouldn't exist if this object is what they claim it to be, just another interstellar comet passing through our cosmic neighbourhood. And here's what makes this moment so significant, so potentially paradigm-shifting. The images all show the same thing: independent observers, using different equipment, from different locations at different times, all capturing identical anomalies. When that happens, when multiple independent sources converge on the same observations, you can't dismiss it as error or misinterpretation. You have to confront what the data is actually showing you. Before we go, I need to know something. Where are you watching this from right now? Drop your location and what time it is where you are in the comments below, because here's what's fascinating. While you've been listening to this, 3i Atlas has travelled another few thousand kilometres through our solar system. Someone watching this in Tokyo is experiencing a different moment of its journey than someone in New York or London or Sydney. We're all tracking the same mysterious visitor, but from different perspectives across this planet. And if you haven't already, hit that subscribe button and turn on notifications. The December 19th observations are happening soon, and when that data drops, you're going to want to be among the first to know what we find. Are we looking at the most exotic comet ever discovered? Or are we witnessing something that will rewrite everything we thought we knew about our place in the universe? Drop your location and local time below. Let's see how global this cosmic mystery has become, and I'll see you in the next one, where we'll be breaking down whatever comes out of those December observations. This is history in the making, folks, and you're here for it. Between November 22nd and November 24th, 2025, several amateur astronomers pointed their telescopes at 3i Atlas and recorded something that stops you cold when you first see it. The object displays a massive tail, stretching millions of kilometers behind it as it moves through space. That part isn't surprising. Comets develop tails. That's what they do when solar radiation and solar wind push gas and dust away from the nucleus. But here's where normal ends and strange begins. 3i Atlas also displays what's called an anti-tail, a structure pointing directly toward the sun rather than away from it, and this isn't a faint, ambiguous feature that might be an optical illusion or viewing geometry effect. This is a strong, persistent, clearly defined stream of material extending approximately 1 million kilometers in the direction of the sun, like headlights on a vehicle driving through the darkness of space. Anti-tails can occur naturally under very specific geometric conditions, but they're rare and they're brief. What we're seeing with 3i Atlas is neither rare nor brief. It's sustained, it's massive, and it defies the physics of how cometary material should behave. Let's talk about the numbers, because the numbers tell a story that words alone can't convey. The main tail, the one pointing away from the sun as expected, extends approximately 5 million kilometers. To put that in perspective that you can actually grasp, if you were travelling at 400 meters per second, which is roughly the speed of sound in air at sea level scaled up considerably, it would take you an entire month to traverse just the anti-tail portion, that 1 million kilometer structure pointing sunward. The full tail would require 5 months of continuous travel at that speed. We're dealing with structures on a scale that dwarfs anything in human experience, and those structures are behaving in ways that challenge our understanding of how matter moves in space when subjected to solar radiation pressure and solar wind. The best image came from Mitsunori Sumura, an amateur astronomer using a half-meter telescope. Modest equipment by professional standards, but more than adequate for capturing detailed observations of bright objects. And 3i Atlas, despite being 300 million kilometers from Earth, roughly twice the distance from Earth to the Sun, is bright enough and structured enough that this equipment reveals extraordinary detail. The image shows a glowing coma surrounding the nucleus, exactly what you'd expect from a comet as volatile ices sublimate and create that characteristic fuzzy atmosphere. But the tail structure is anything but characteristic. The main tail is tight and bright, more collimated than the diffuse fans typical of cometary tails, suggesting that whatever is producing it is being expelled in a more directed, more organised manner than random sublimation would create. and that anti-tail, those cosmic headlights, persist with an intensity and extension that shouldn't be possible given what we understand about the forces at work. Now here's where the physics becomes problematic for anyone trying to maintain that 3I Atlas is a natural object following natural processes. For material to move sunward against the solar wind, it needs momentum, substantial momentum. The solar wind at Earth's distance travels at approximately 400 kilometers per second, and while it's tenuous, just a few particles per cubic centimeter, it exerts pressure on anything it encounters. For the anti-tail to push through that solar wind and extend 1,000,000 kilometers toward the sun, the material composing it would need to be traveling significantly faster than the solar wind itself, or it would need to be so dense, so massive, that the solar wind can't deflect it. Either scenario creates problems. Thermal sublimation of ice, the process that powers normal cometary activity, produces gas velocities of maybe a few hundred meters per second at most, perhaps up to 400 meters per second under optimal conditions. That's roughly 1,000 times slower than the solar wind. The ram pressure, the resistance encountered when moving through a medium, scales with the square of velocity, which means that for the anti-tail material to maintain its sunward trajectory against the solar wind, its mass density would need to be approximately 1,000,000 times higher than the solar wind itself. Let's work through what that implies. If this anti-tail is produced by natural cometary outgassing, the kind of sublimation-driven activity we see on every other comet we've studied, then 3I Atlas would need to be expelling material at a rate that's almost incomprehensible. The calculations suggest a mass loss flux of approximately 200 tons per second per square meter, sustained over the cross-sectional area of the anti-tail structure. That structure, based on the images, has dimensions on the order of hundreds of thousands of kilometers. When you integrate the mass loss over the entire structure and over the time period during which this activity has been observed, you arrive at a total mass loss of several billion tons. Let that number settle for a moment. Billion, with a B. Several billion tons of material expelled in approximately 2 months. Now compare that to the estimated total mass of 3I Atlas, which orbital dynamics and earlier observations suggest is around 33 billion tons. If the anti-tail is natural, then this object has lost roughly 10% of its entire mass in 2 months. That's not gradual sublimation. That's catastrophic disintegration. And yet, the nucleus remains intact. The object hasn't fragmented. The brightness hasn't decreased in the way you'd expect from such massive material loss. The mathematics and the observations don't align. There's a detail in the timeline that's crucial to understanding what's happening here. During the months of July, August, and September 2025, when 3I Atlas was farther from the Sun and consequently experiencing less solar heating, the object showed no non-gravitational acceleration, 0. Its trajectory matched perfectly with predictions based solely on gravitational influences from the Sun and planets. No unexplained deviations, no mysterious velocity changes. It moved exactly as a passive chunk of ice and rock should move when subjected only to gravity. But something changed in October. As 3I Atlas approached Perihelion, its closest point to the Sun, observers began detecting non-gravitational acceleration, a deviation from the purely gravitational trajectory that indicates something is producing thrust. And this wasn't a subtle effect barely above the noise threshold. The Jet Propulsion Laboratory's Horizon system, which tracks the positions and trajectories of solar system objects with extraordinary precision, now reports this acceleration as highly significant, quantified at 10 standard deviations above background uncertainty. In statistical terms, that's not marginally significant. That's slam dunk certain. Something is pushing 3I Atlas in ways that gravity alone can't explain. Here's where the story takes a turn that should make everyone sit up and pay attention. Before 3I Atlas reached Perihelion, Professor Avi Loeb from Harvard, who's become something of a controversial figure in astronomy for his willingness to consider hypotheses that more conservative colleagues dismiss, made a prediction. He noted that perihelion would occur when 3I Atlas was behind the Sun from Earth's perspective, creating an observational gap during which we couldn't track the object directly. And he suggested that if 3I Atlas were artificial rather than natural, if it possessed any kind of propulsion or guidance capability, that gap would be the perfect moment to execute a maneuver. Change trajectory, adjust velocity, deploy smaller objects. Whatever action might be part of its mission parameters, The perihelion passage while hidden behind the Sun would be the ideal time to act without being observed in real time. At the time, this seemed like interesting speculation, the kind of thought experiment that's valuable for considering possibilities even if they're unlikely. But now, with the benefit of hindsight and access to the post-perihelion data, that prediction looks uncomfortably prescient. Because 3I Atlas did change trajectory, the non-gravitational acceleration that appeared near perihelion has altered the object's path in measurable, significant ways. The implications of that trajectory change depend entirely on your interpretation of what's causing the acceleration. If you believe this is natural outgassing, sublimating ice-creating jets that push the object around like tiny rocket engines, then the trajectory change is interesting, but not fundamentally mysterious. Comets change trajectories all the time due to outgassing. It's expected. But if the mass loss required to produce the observed acceleration through natural processes is as extreme as the calculations suggest, if 3I Atlas would need to have lost 10% of its mass to create the observed effects through thermal sublimation alone, then you start questioning whether the natural explanation actually works. Because the object shows no signs of that kind of catastrophic mass loss. It's not fragmenting, it's not dimming, it's not behaving like something that just vented billions of tons of material into space. Which raises the alternative interpretation, the one that makes most scientists uncomfortable, but that fits the observations with far fewer problematic assumptions. What if the acceleration isn't caused by natural outgassing at all? What if it's propulsion? Consider the energetics from an engineering perspective. If you wanted to produce the observed acceleration using a technological propulsion system, rather than relying on natural ice sublimation, you'd need far less mass. Chemical rockets, the kind we use to launch spacecraft from Earth, achieve exhaust velocities of several kilometers per second, roughly 10 times faster than thermal gas from sublimating ice. That factor of 10 in velocity translates to a 100-fold reduction in the mass required to produce the same thrust, because momentum is mass times velocity. So where natural outgassing would require billions of tons of expelled material, chemical propulsion could achieve the same acceleration with only tens of millions of tons. That's still substantial, but it's within the realm of plausibility for an object with a total mass of 33 billion tons. You wouldn't be losing 10% of your mass, you'd be losing a fraction of a percent, well, within the margins that wouldn't produce obvious observational signatures. And if you move beyond chemical propulsion to electric propulsion, ion drives or plasma thrusters that accelerate particles to even higher velocities using electromagnetic fields, the mass requirements drop further. Ion drives can achieve exhaust velocities of tens of kilometers per second. At those speeds, you could produce the observed acceleration with mass expenditure measured in hundreds of thousands of tons rather than billions. The required propellant fraction becomes trivially small, easily hidden within the normal uncertainties of mass estimates. The question of how to distinguish between these scenarios, natural outgassing versus technological propulsion, isn't just academic. It determines whether we're observing a weird but fundamentally normal comet, or whether we're witnessing something unprecedented in human history. And the answer lies in measurements we haven't yet made with sufficient precision. Specifically, we need spectroscopic observations of the jets themselves, detailed measurements of the velocities at which gas is being expelled from the nucleus. If the outgassing velocities match what we'd expect from thermal sublimation, a few hundred meters per second consistent with the temperature of the surface ices, then the natural explanation holds despite its problems. But if the velocities are higher, if we detect exhaust speeds measured in kilometers per second rather than meters per second, then we're looking at something other than sublimation. We're looking at directed acceleration of particles through some mechanism that adds energy beyond simple thermal processes. Those measurements are coming. Multiple observatories have 3I Atlas in their sights, and high-resolution spectroscopy is planned for December when the object makes its closest approach to Earth. The data from those observations will either confirm the natural interpretation or blow it apart entirely. The images keep coming in, and they all tell the same story. Paul Craig's, observing on November 22nd, captured photographs showing what appears to be an elongated structure, though there's debate about whether this represents the actual shape of the nucleus or is an artifact of motion blur during the exposure. Peter Carson Lee, observing from Spain on the same night, obtained independent confirmation of the tail and anti-tail structures. Elena Walter, working from Chile on November 24th, added another data point to the growing collection. The geographic and temporal distribution of these observations matters because it rules out localized effects or systematic errors tied to specific equipment or locations. When observers separated by thousands of kilometers and using different telescopes all see the same features, you can be confident those features are real. The anti-tail isn't an illusion. The extended main tail isn't processing artifact. These structures exist, and they demand explanation. Now we need to address what might be the single most compelling anomaly in the entire 3I Atlas story, something so statistically improbable that it stretches coincidence past the breaking point. This involves orbital mechanics, gravitational physics, and a concept called the Hill radius that determines where one body's gravitational influence dominates over another's. Jupiter, the largest planet in our solar system, has a Hill radius that extends approximately 53.5 million kilometers from its center. Inside that radius, Jupiter's gravity is the dominant force. Outside it, the Sun's gravity takes over. The Hill radius isn't a sharp boundary, it's a gradual transition zone, but it represents the region where objects can maintain stable orbits around Jupiter rather than being pulled away by the Sun's stronger but more distant gravitational field. This is why Jupiter has so many moons. They orbit within the Hill radius, where Jupiter's gravity keeps them bound despite the Sun's presence. According to calculations based on 3I Atlas's trajectory, as it was understood in late October, the object was projected to pass Jupiter on March 16, 2026, at a distance of 53.445 million kilometers. Note that number. Now compare it to Jupiter's Hill radius at that time, which orbital mechanics calculations place at 53.502 million kilometers. The difference is 57,000 kilometers. On cosmic scales, that's nothing. That's an error margin of about 0.1%. 3I Atlas, according to these projections, will skim the very edge of Jupiter's Hill radius, threading a needle through space with precision that seems almost impossible for a natural object on a random trajectory. The statistical probability of this happening by chance, of an interstellar visitor arriving from the depths of space and just happening to pass Jupiter at exactly the distance where gravitational dynamics create interesting effects, is vanishingly small. Calculations suggest odds of less than 4%, 4 in 100,000. That's not impossible, but it's improbable enough to make you question whether chance is really the explanation. But here's where the story gets even stranger. Moving from improbable coincidence into territory that feels almost conspiratorial, except that it's documented in official data sources anyone can verify. When Professor Loeb raised questions about this Hill radius coincidence, when he started discussing it publicly and asking NASA for comment about the precision of the trajectory match, something odd happened. The numbers changed. The JPL Horizon system, which had been reporting one set of orbital parameters and projecting the close Hill radius encounter, suddenly updated its calculations. The revised trajectory placed 3I Atlas slightly outside Jupiter's Hill radius, no longer threading that needle, but passing at a distance that would keep it clear of Jupiter's gravitational dominance region. On the surface, this might seem like normal scientific updating, refining calculations as more data comes in, improving precision. But the timing raised eyebrows. The update came shortly after the Hill radius coincidence became a topic of public discussion, and the methodology used in the updated calculations seemed questionable to some independent analysts. The revised JPL model apparently uses mass loss parameters derived from observations taken when 3I Atlas was farther from the Sun, extrapolating those rates forward to predict behavior near perihelion. But observations from Hubble and other facilities suggest that 3I Atlas brightened far more rapidly near perihelion than those extrapolations would predict, indicating that the actual mass loss or activity level was higher than the model assumes. If you correct for that discrepancy, if you use the actual observed brightness evolution rather than the extrapolated model, the trajectory calculations shift back toward the original numbers, back toward that precise Hill radius encounter. So which calculation is correct? The one that shows the improbable coincidence, or the revised one that makes the coincidence disappear? The answer will come from observations, not models. As Professor Loeb noted in his public statements, the orbit doesn't care what NASA's models say. Reality will decide. In March 2026, when 3I Atlas actually reaches Jupiter's vicinity, We'll measure its position with precision, and we'll know definitively whether it passes inside or outside the Hill radius. The data will speak for itself. But why does this matter? Why is the Hill radius encounter significant beyond just being a statistical oddity? Because of what it would enable. If 3I Atlas passes inside Jupiter's Hill radius, even briefly, it enters a region where deploying smaller objects becomes vastly more efficient. Anything released from the main body while inside that radius would naturally tend to remain in Jupiter's gravitational sphere of influence, rather than being pulled back toward the Sun. You could deploy probes or instruments or whatever payload the object might be carrying, and they would settle into relatively stable orbits around Jupiter, with minimal additional propulsion required. The Lagrange points, those special locations where the gravitational forces of Jupiter and the Sun balance in ways that allow objects to maintain fixed positions relative to both bodies, sit within or near the Hill radius. The L1 and L2 points in particular are valuable for long-term observation platforms because they require almost no fuel to maintain position. A probe placed at Jupiter's L1 or L2 point could observe the Jovian system and the inner solar system indefinitely with minimal station-keeping requirements. If you were designing a mission to survey our solar system, if you wanted to establish a permanent observation presence that could function for millions of years, the Jupiter Lagrange points would be obvious choices for deployment locations. And that brings us to the uncomfortable question that underlies all of this discussion. The question that most scientists prefer to avoid asking directly because it ventures so far beyond the boundaries of conventional scientific discourse. Is 3I Atlas artificial? Is it a probe, a spacecraft, a technological artifact sent by some intelligence that existed in the distant past or perhaps still exists somewhere among the stars? The evidence doesn't prove this interpretation, not yet, not definitively. But the evidence is consistent with it in ways that are becoming harder to dismiss as coincidence. The electromagnetic pulses from the core, the controlled outgassing that maintains rotational stability, the trajectory that threads through Jupiter's Hill radius with improbable precision, the acceleration that appeared exactly when and where it would be most useful for altering the object's path, the anti-tail that requires either catastrophic mass loss or directed propulsion to explain. Each individual anomaly might have a natural explanation, but collectively the pattern they form looks less like nature and more like design. December 2025 is shaping up to be a crucial month, potentially the month when this question gets answered, or at least when the available evidence tips decisively in one direction or another. On December 19th, 3I Atlas will make its closest approach to Earth, passing at a distance of 269 million kilometers. That's still distant by terrestrial standards, roughly the distance from Earth to Mars at their closest approach, but it's close enough for our most powerful telescopes to obtain images with unprecedented resolution. The Hubble Space Telescope has observation time allocated. The James Webb Space Telescope, with its infrared capabilities that can peer through the coma to see the nucleus itself, is preparing observations. Ground-based facilities with adaptive optics that can compensate for atmospheric distortion are ready to capture whatever details emerge. And spacecraft in the inner solar system, missions like Juno orbiting Jupiter and Psyche en route to its asteroid target, might contribute astrometric data, precise position measurements that help refine the trajectory calculations and determine whether the Hill radius encounter is real or artifact. The scientific community approaches these observations with a mixture of excitement and apprehension. Excitement because we might finally get data that resolves the ambiguities, that tells us definitively whether 3I Atlas is weird comet or something far more significant. Apprehension because either answer carries profound implications. If it's natural, if all these anomalies can be explained by exotic but understood physics, then we've learned that the universe is even stranger than we thought, capable of producing organized, persistent structures through processes we're only beginning to understand. But if it's artificial, if the evidence becomes overwhelming that this object represents technology from another intelligence, then everything changes. Our place in the cosmos changes. Our understanding of whether we're alone changes. The questions we ask about the universe and our role in it change. There's no neutral outcome here. Whichever way the data points, the implications are transformative. Some researchers have started thinking ahead to what comes after the December observations, assuming they don't provide definitive answers. There's talk of a dedicated mission, a spacecraft designed specifically to intercept 3I Atlas and make close-up measurements that remote sensing can't achieve. The engineering is challenging but not impossible. A small probe using solar sails or ion propulsion could potentially catch up to 3i Atlas before it exits the inner solar system, though the launch window is closing rapidly as the object moves farther from Earth and the Sun. Such a mission could carry instruments to analyse the composition of the outgassing directly, measuring exhaust velocities and chemical signatures. It could deploy penetrators to probe beneath the surface ice and determine the structure and composition of deeper layers. It could even attempt to land on the surface, though the low gravity and potential for active venting would make that risky. The scientific return from such a mission would be extraordinary, potentially answering questions that decades of remote observation couldn't resolve. But the cost would be substantial, measured in billions of dollars, and the timeline would be tight, requiring design and construction on an accelerated schedule that increases risk. The decision about whether to pursue such a mission will be made at political levels by space agency administrators and government officials who must balance scientific priorities against budget realities and public interest. The case for the mission rests on the potential significance of what we might learn. If there's any reasonable chance that 3i Atlas is artificial, that it represents our first confirmed encounter with technology from another civilization, then the mission becomes not just scientifically valuable, but historically imperative. The knowledge we could gain would be priceless, transforming our understanding of intelligence, technology, and the prevalence of advanced civilizations in the galaxy. But if the likelihood of artificial origin is low, if this is probably just a really weird comet, then the cost-benefit analysis becomes less favourable. The same resources could fund multiple missions to other targets, with more certain scientific returns. The debate over these priorities is already underway, playing out in planning committees and budget negotiations and public discourse about what humanity's exploration priorities should be. Meanwhile, 3i Atlas continues its journey, indifferent to our debates and speculations. It moves through space at roughly 20 kilometers per second relative to the Sun, covering 1.7 million kilometers each day, steadily approaching the moment when it will either confirm our assumptions or shatter them. The electromagnetic pulses continue their mysterious rhythm, the anti-tail streams sunward with impossible persistence. The nucleus remains intact despite the apparent violence of the outgassing that's supposedly powering all this activity. Every day brings new observations, new data points, new pieces of a puzzle that refuses to resolve into a clear picture. And every day the sense grows among those paying close attention that we're watching something unprecedented unfold, that 3i Atlas represents a threshold moment in humanity's relationship with the cosmos, the point where we transition from wondering if we're alone to grappling with evidence that might answer that question definitively. The story isn't over, not by a long measure. The next few weeks will bring new observations, new analyses, new debates about interpretation and methodology. March 2026 will show us whether the Hill radius encounter is real, and whether anything happens when 3i Atlas passes through that region of gravitational complexity. The trajectory will continue to be refined as more position measurements accumulate. The spectroscopic data will either confirm natural outgassing velocities or reveal something more exotic. And through all of it, the fundamental question will persist, hanging over every observation and every analysis like a weight that can't be ignored. What is 3i Atlas really? Is it a messenger from the stars, a technological artifact carrying information or capabilities we can barely imagine, sent by intelligence that existed when our sun was young and Earth was still forming? Or is it a natural wonder, a cosmic accident that happens to display characteristics that mimic design, teaching us that nature's creativity exceeds our categories and expectations? The answer matters, and the answer is coming. The answer is coming, but while we wait for December's observations to potentially resolve some uncertainties, the data we already have keeps revealing new layers of complexity that deepen rather than resolve the mystery. Let's talk about what the trajectory analysis actually shows when you dig into the numbers with the kind of rigor that peer-reviewed science demands. The non-gravitational acceleration that appeared near Perihelion isn't a single event, a brief burst of activity that altered the path and then ceased. It's ongoing. The JPL Horizon system updates its calculations regularly as new position measurements come in from observatories around the world, and those updates show that the acceleration continues, though its magnitude has changed in ways that themselves require explanation. On October 30th, 2025, shortly after perihelion, the radial acceleration component, designated A1 in the orbital mechanics nomenclature, was measured at 1.66 times 10 to the negative 6th astronomical units per day squared. That's the rate at which the object's distance from the Sun was changing in ways that couldn't be explained by solar gravity alone. But by November 24th, when the calculations were updated with additional observations, that A1 value had dropped to 4.7 times 10 to the negative 7th astronomical units per day squared, a decrease by a factor of approximately 4. What does that mean in physical terms? If the acceleration is caused by outgassing, by ice sublimating and creating jets that push the object around, then you'd expect the acceleration to decrease as the object moves farther from the Sun and solar heating diminishes. That's basic physics. Less heat means less sublimation means weaker jets means lower acceleration. So a factor of 4 decrease over the course of a month as 3I Atlas moved from approximately 1.4 astronomical units at perihelion to roughly 1.8 astronomical units by late November might seem consistent with natural processes. The intensity of solar radiation follows an inverse square law, dropping by a factor of 1.6 as distance increases from 1.4 to 1.8 AU. And if you account for the nonlinear relationship between surface temperature and sublimation rate, a factor of 4 decrease in acceleration is at least plausible. But here's what troubles researchers who've been tracking this closely. The decrease isn't smooth. It's not a gradual decline following a predictable curve based on solar heating models. Instead, the acceleration seems to drop in steps, periods of relative stability punctuated by sudden changes that happen too quickly to be explained by the slowly changing solar radiation environment. It's almost as if something is turning on and off, adjusting thrust levels in response to some criterion we don't understand. Natural outgassing can be episodic, certainly. Comets have outbursts, sudden increases in activity when subsurface ice is exposed, or when cracks open up to allow trapped gas to escape. But those events typically show up as brightness increases, temporary brightenings of the coma as additional dust and gas are released. The stepwise changes in 3I Atlas's acceleration don't correlate obviously with brightness variations, suggesting that whatever causes the acceleration changes isn't the same process that creates the visible coma. That disconnect between acceleration and brightness is another small anomaly to add to the growing list, another detail that fits uncomfortably with the natural comet interpretation. The trajectory calculations themselves have become a subject of intense scrutiny and, frankly, controversy. When JPL updated its orbital model in late November, reducing the projected Hill radius encounter from a near-certain passage inside Jupiter's gravitational dominance zone to a near miss that would keep 3I Atlas just outside that boundary, the change rested on assumptions about mass loss rates and how those rates affect the object's motion. Here's the fundamental issue. When a comet loses mass through outgassing, the escaping gas carries momentum, and by Newton's third law, that momentum transfer accelerates the nucleus in the opposite direction. The magnitude of that acceleration depends on how much mass is being expelled and how fast it's moving. If you underestimate the mass loss rate, you'll underestimate the acceleration. If you overestimate the exhaust velocity, you'll overestimate the acceleration. The JPL model uses parameters derived from brightness observations at larger distances, when 3I Atlas was less active, and extrapolates those parameters to predict behavior near perihelion. But multiple independent observers have noted that 3I Atlas brightened far more rapidly as it approached the Sun than the extrapolation predicted. The Hubble Space Telescope captured images showing enhanced activity. Ground-based photometry showed brightness increases exceeding model predictions. These observations suggest that the actual mass loss near perihelion was higher than the JPL model assumes, which would imply stronger outgassing and consequently larger non-gravitational accelerations. If you recalculate the trajectory using mass loss rates consistent with the observed brightness evolution rather than the extrapolated model values, the projected flyby distance shifts back toward the Hill radius boundary. The difference between these two approaches, the extrapolation-based model versus the observation-based correction, amounts to tens of thousands of kilometers in the predicted Jupiter flyby distance, and those tens of thousands of kilometers are exactly the margin that determines whether 3I Atlas passes inside or outside the Hill radius. It's uncomfortably convenient that the model revision happened to shift the prediction in the direction that makes the Hill radius coincidence disappear, and it's understandable that some researchers question whether the revision was driven by data or by a desire to avoid an uncomfortable implication. Let's be clear about what we're suggesting here, because the accusation is serious and deserves to be stated plainly. Is NASA deliberately manipulating trajectory calculations to hide evidence of artificial origin? The answer, almost certainly, is no. Institutional conspiracy requires coordination and secrecy that's nearly impossible to maintain, especially in an organization as large and diverse as NASA, where different groups and individuals have competing interests and perspectives. What's more likely is that different analysts are making different judgment calls about how to weight various data sources and how to extrapolate from limited observations to predict future behavior. Those judgment calls can be influenced, consciously or unconsciously, by prior beliefs about what's plausible and what's not. If you start from the assumption that 3I Atlas is a natural comet, then extrapolating mass loss rates from earlier observations and assuming smooth, predictable behavior near perihelion seems reasonable. But if you're open to the possibility that the object might be artificial, that it might execute maneuvers or adjust its activity level in response to internal programming, then you'd place more weight on the actual observed brightness evolution and less on model extrapolations. Neither approach is wrong exactly, but they lead to different predictions, and the difference matters enormously when those predictions determine whether an improbable coincidence is real or artifact. The reality check will come from observation, not calculation. In March 2026, when 3I Atlas reaches Jupiter's vicinity, we'll measure its position with high precision using multiple independent techniques. Radio telescopes can ping the object with radar and measure the return signal timing to determine distance with centimeter-level accuracy. Optical astrometry from multiple observatories will triangulate position against background stars. Spacecraft in the outer solar system, missions like Juno that are already in Jupiter orbit and have precise trajectory knowledge, might be able to observe 3I Atlas and provide additional data points. With all those measurements combined, we'll know the flyby distance to within a few thousand kilometers, maybe better. If it's inside the Hill radius, then the coincidence is real. The statistics are as improbable as calculated, and we have to confront what that means. If it's outside, even by a small margin, then maybe the revised JPL model was correct and this particular anomaly evaporates. But even in that case, even if the Hill radius coincidence turns out to be artifact of preliminary calculations, all the other anomalies remain. The electromagnetic pulses, the anti-tail, the controlled rotation, the structured radio transmission from perihelion, none of those go away just because one prediction proves incorrect. There's a broader methodological question here about how science should proceed when confronting potentially unprecedented phenomena. The standard approach, the one taught in every research methods course, is to assume the simplest explanation that accounts for the observations, to require extraordinary evidence before accepting extraordinary claims, to remain skeptical of interpretations that challenge well-established theories. That approach has served science well. It's protected us from countless false leads and prevented the field from being derailed by every anomaly or unexpected observation. But it also has limitations, particularly when the phenomenon you're studying is genuinely novel, something outside the envelope of previous experience. If you demand that every unusual observation be explained within existing frameworks, if you refuse to seriously consider alternatives that don't fit conventional categories, then you risk missing genuinely revolutionary discoveries precisely because they don't fit expectations. The challenge is finding the right balance between healthy skepticism and premature dismissal, between remaining open to possibilities and not being so open-minded that you accept claims without adequate support. In the case of 3I Atlas, different researchers and institutions are calibrating that balance differently. The conservative position, exemplified by most official NASA statements and much of the published scientific literature, emphasizes that while the object exhibits unusual characteristics, those characteristics don't yet meet the threshold for concluding artificial origin. Every anomaly has potential natural explanations, even if those explanations require somewhat special circumstances or invoke processes we don't fully understand. The electromagnetic pulses could be natural resonance phenomena. The anti-tail could be unusual grain properties or viewing geometry effects. The trajectory optimization could be selection bias or coincidence. The non-gravitational acceleration could be asymmetric outgassing. None of these explanations is entirely satisfying, none fits perfectly, but collectively they provide enough plausibility that the artificial hypothesis can be held at arm's length as an interesting but unproven alternative. This position isn't unreasonable, it's how science normally operates, conservatively updating beliefs only when evidence becomes overwhelming. The alternative position, held by a smaller but growing faction within the research community, argues that conservatism has tipped into denial, that the cumulative weight of anomalies has crossed the threshold where the artificial hypothesis deserves serious investigation, rather than being treated as a last resort invoked only after every conceivable natural explanation has been exhausted. These researchers point out that if we wait for absolute proof before considering artificial origin seriously, we'll never get that proof because we won't deploy the instruments and missions needed to obtain it. If 3i Atlas is artificial but we refuse to treat it as such because no single observation definitively proves it, then we'll watch it exit the solar system without ever making the measurements that could have confirmed its nature. And if it does turn out to be artificial, if future discoveries or historical analysis eventually reveals that this was our first encounter with extraterrestrial technology, then the scientific community will have to explain why it failed to recognize the significance of what was happening in real time, why it allowed caution to prevent investigation of what might be the most important discovery in human history. Both positions have merit, and the tension between them reflects fundamental questions about scientific methodology that don't have simple answers. How do you investigate something unprecedented when your methods and frameworks are built on precedent? How do you remain appropriately skeptical without becoming so conservative that you can't recognize genuine novelty when it appears? These questions aren't unique to the 3i Atlas situation. They arise whenever science confronts phenomena at the boundaries of known territory. But they're particularly acute here because the stakes are so high. If this is artificial, the implications extend far beyond astronomy into philosophy, theology, politics, culture, every domain of human thought and activity. The pressure to get the answer right, to neither cry alien prematurely nor miss the significance of a genuine contact, creates an almost paralyzing uncertainty that makes definitive statements difficult even when the evidence points in clear directions. Let's return to the observations themselves, to the concrete data that grounds all this speculation and debate. The images captured in late November show not just the anti-tail but also fine structure within both the main tail and the sunward-pointing structure. The main tail isn't uniform. It shows striations, parallel lanes of brighter and dimmer material that suggest the outgassing isn't happening uniformly across the nucleus surface, but instead comes from discrete active regions. That by itself isn't unusual. Many comets show jets from specific vents. But the geometry of the striations in 3i Atlas's tail is peculiar. They're too regular, too evenly spaced, almost like the teeth of a comb. Natural jets typically create fan-shaped structures that spread and dissipate as material moves away from the nucleus. The parallel striations suggest that the jets maintain their directionality over enormous distances, millions of kilometers, which requires either unusual grain properties that prevent lateral spreading, or some mechanism that collimates. The flow keeps it confined to narrow streams. The anti-tail shows different structure. Rather than striations, it appears more uniform but with periodic variations in brightness along its length, regularly spaced bright and dim regions like beads on a string. These variations could represent pulsed ejection, periodic bursts of material released in rhythmic sequence rather than continuous flow. If you measure the spacing between bright regions and compare it to the object's known velocity, you can estimate the time interval between pulses. The preliminary analysis suggests a period of approximately 40 to 50 minutes, remarkably consistent given the uncertainties in the measurements. What could cause such regular pulsing? If it's natural, maybe it's related to rotation, specific active regions on the nucleus rotating into and out of sunlight in a regular cycle. But 3i Atlas's rotation period, as measured from brightness variations, is longer than the pulse period in the anti-tail, so simple rotation can't explain it. You'd need multiple active regions spaced around the equator, firing in sequence as they rotate past some specific solar angle, and you'd need that geometry to remain stable over weeks despite the thermal and mechanical stresses the object is experiencing. It's possible, but it requires a fairly specific set of circumstances. The alternative interpretation is that the pulsing represents regulated release, a valve opening and closing on a fixed schedule, expelling material in controlled bursts rather than continuous flow. From an engineering perspective, pulsed operation offers advantages for systems that need to maintain precise control over thrust or material release. It's easier to measure and adjust discrete pulses than continuous flow. It allows for cooling periods between active phases that might be necessary if the release mechanism generates heat, and it provides a clear signature that could be used for communication or synchronization if multiple systems needed to coordinate their activities. None of this proves the pulsing is artificial, but it's consistent with artificial operation in ways that natural processes typically aren't. Natural phenomena tend towards smooth variation or chaotic fluctuation. Regular periodicity at timescales that don't match obvious physical cycles like rotation or orbital period is relatively rare in uncontrolled systems. There's been discussion in the research community about attempting to detect the outgassing directly using spectroscopic techniques that can measure Doppler shifts from the jets. When gas moves toward or away from the observer, the wavelengths of light it emits get shifted by an amount proportional to the velocity. By measuring these Doppler shifts for specific emission lines, you can determine how fast the gas is travelling. This is routine for studying stellar atmospheres and galactic rotation, but it's more challenging for comets because the emission lines are often faint and the velocity differences are small. But with 3I Atlas approaching its closest point to Earth in mid-December, the opportunity for high-resolution spectroscopy is optimal. Several teams have observation time allocated on major telescopes, instruments capable of spectral resolution fine enough to detect velocity shifts corresponding to a few hundred meters per second. If the measurements show gas velocities consistent with thermal sublimation, around 200 to 400 meters per second that supports the natural interpretation. But if the velocities are significantly higher, approaching a kilometer per second or beyond, then thermal processes can't explain it, and you need to invoke some form of active acceleration. The expectation is building toward those December observations with an intensity that's unusual for astronomical research. Normally, telescope time is allocated months in advance. Proposals are reviewed for scientific merit, and the observations themselves are routine, just another night collecting data on whatever target has been assigned. But the 3I Atlas observations feel different. There's an awareness among the observers that what they're measuring might be historically significant, that the spectra or images they capture could be the data points that tip the interpretation one way or another. Some have described it as similar to the anticipation before the first gravitational wave detection or the first direct image of a black hole, moments when decades of theoretical work and instrumental development converge on a measurement that could confirm or revolutionize understanding. The difference is that those earlier breakthrough observations were measuring phenomena we were confident existed, we just needed the technology to detect them. With 3I Atlas, we're not sure what we're measuring. We're trying to determine the nature of the phenomenon itself, not just observe a known thing in a new way. The public awareness of all this remains limited, which is both frustrating and understandable. Frustrating because this might be one of the most significant events in modern astronomy, potentially in all of human history if the artificial hypothesis proves correct, and yet most people have never heard of 3I Atlas. Understandable because the story's complex, the evidence is ambiguous, and communicating uncertainty while maintaining interest is extraordinarily difficult. The media tends toward binary narratives, either dramatic revelation or nothing worth reporting. The nuanced middle ground, where we have intriguing observations that suggest something unusual is happening, but don't yet provide definitive answers, that's hard to package into compelling headlines. A few science journalists have been covering the story, writing detailed pieces that explore the various anomalies and the debates about interpretation, but those articles don't typically break through to mainstream awareness. The general public won't likely hear about 3I Atlas unless either the December observations provide smoking gun evidence of artificial origin, or the March Jupiter flyby produces dramatic visible events. And maybe that's appropriate. Science proceeds at its own pace, following evidence rather than public attention. The question of what 3I Atlas represents will be answered by careful observation and rigorous analysis, not by opinion polls or social media trends. But there's also value in broader awareness, in having public discourse catch up with scientific discovery, so that when significant findings emerge, there's context for understanding them. The discovery that we're not alone in the universe, that intelligence exists or existed elsewhere among the stars, shouldn't come as a complete surprise sprung on an unprepared public. It should be the culmination of accumulating evidence that people have been following and thinking about, so the final confirmation feels like resolution rather than shock. Perhaps the months between now and March serve that function, a grace period where the question can be raised and considered without the pressure of immediate definitive answers, allowing both scientists and public to contemplate what it might mean if 3i Atlas turns out to be artificial. The implications of that possibility extend in directions that are difficult to fully map. Start with the most obvious question. If 3i Atlas is artificial, who built it? The exotic isotopes in its core suggest formation in a stellar environment very different from our Sun's, probably near a massive star that later exploded as a supernova. The age estimates, based on cosmic ray exposure and isotopic decay, suggest the object has been travelling through space for a minimum of tens of millions of years, possibly hundreds of millions or even billions. Whatever civilization created it, if any did, existed in the distant past. They might have evolved on a planet orbiting a star that no longer exists in any recognizable form. They might have achieved technology we can barely imagine and then vanished, either through catastrophe or transformation, or simple migration to other regions of the galaxy. Or they might still exist, somewhere out there, maintaining networks of probes and observatories across countless star systems, collecting data on a timescale that makes our entire civilization look like a brief moment. The technology implied by an artificial 3i Atlas would be substantial, but not necessarily beyond what we might achieve ourselves in a few more centuries of development. The ability to construct objects that function reliably for millions of years requires materials science and engineering, beyond our current capabilities but not beyond theoretical possibility. Systems designed for extreme durability, minimal maintenance, autonomous operation, these are engineering challenges we can conceptualize even if we can't yet implement them. The propulsion system, whether chemical or electric or something more exotic, represents technology we either have in primitive form or can envision developing. The information storage and processing capacity needed to maintain a mission across geological timescales is daunting, but again not impossible in principle. What would be truly impressive isn't any single technological component, but rather the integration, the systems engineering that coordinates everything into a package capable of crossing interstellar distances and operating autonomously in environments that would destroy anything we've built. That level of sophistication suggests a civilization with centuries or millennia of spacefaring experience, one that solved problems we're only beginning to recognize. But here's the more unsettling thought. If 3i Atlas is artificial, it's probably not alone. Any civilization capable of sending probes to other star systems would likely send many such probes, not just one. The galaxy contains hundreds of billions of stars, and surveying even a tiny fraction of them would require millions of probes deployed over immense timescales. We're detecting 3i Atlas only because it happened to pass close to our Sun, and our instruments happen to be capable of seeing it. How many others have passed through our solar system in the past, before we had telescopes, or even before our species existed? How many are passing through right now on trajectories that don't bring them close enough for detection? How many are stationed in the outer solar system, perhaps in the Oort cloud or Kuiper belt, observing us from distances where we'd never noticed them? These questions sound paranoid, like conspiracy thinking, but they're actually just logical extensions of the possibility that one such object exists. If intelligence somewhere developed the capability and motivation to explore the galaxy through autonomous probes, then probability suggests we're surrounded by their creations, most of them invisible to us, a few occasionally passing close enough to notice. That possibility transforms how we think about our solar system. Instead of pristine wilderness, unexplored territory where we're the first intelligence to venture, it becomes something more like settled land where we're late arrivals, moving into a space where others have been present for longer than we can measure. The psychological impact of that realization might be profound. Humanity has always defined itself partly through the frontier narrative, the idea that we're expanding into new territory, discovering what lies beyond known boundaries. If the territory has already been explored, already been catalogued by intelligences that preceded us, then the frontier isn't really frontier. We're not discovering, we're rediscovering. We're following paths that others mapped millions of years before our ancestors climbed down from trees. There's something humbling and almost melancholy in that recognition, a loss of the cosmic innocence that assumed we were first, or at least early in the story of intelligence exploring the universe. On the other hand, if the galaxy contains networks of ancient probes, that has optimistic implications too. It means intelligence can survive long enough to develop such capabilities. It means technological civilizations don't necessarily destroy themselves shortly after achieving spaceflight, that the pessimistic scenarios where nuclear war or environmental collapse or AI emergence inevitably end civilizations before they mature aren't universal outcomes. At least one civilization, maybe many, survived long enough to build machines that still function millions of years later. That's evidence for the possibility of long-term survival, for the chance that we too might navigate the challenges ahead and eventually join the community of species or post-species entities that have achieved stable presence in the galaxy. The probes themselves might even serve beneficial functions. Perhaps they're warning systems detecting dangerous phenomena and broadcasting alerts. Perhaps they're repositories, storing knowledge from civilizations that no longer exist, preserving information against the heat death of the universe. Perhaps they're communications relays, parts of a galactic internet that allows coordination and information sharing across light-year distances. We tend to assume that alien technology would be threatening, an invasion or conquest scenario, but there are many other possibilities, most of them benign or even beneficial. The immediate question, the one that matters for the next few months, is what happens if 3I Atlas does pass through Jupiter's Hill radius, and what we should look for as indicators that something significant is occurring. The deployment scenario, releasing smaller probes or instruments while inside the region where Jupiter's gravity dominates, wouldn't necessarily be visible from Earth. If the objects being deployed are small, maybe a few meters across or even smaller, and if they're dark, low albedo surfaces that don't reflect much sunlight, we might not see them at all. What we might detect instead are secondary effects. Changes in the electromagnetic emissions from 3I Atlas's power is diverted to deployment systems, brightness variations as covers are opened, or components are released, spectroscopic signatures of gases or materials released during the deployment process, or, if we're very fortunate, direct detection of the deployed objects if they happen to pass in front of background stars or if they emit their own electromagnetic radiation. The spacecraft already in Jupiter's vicinity offer potential observation platforms. Juno, NASA's mission currently in polar orbit around Jupiter, carries instruments designed to study the planet's magnetic field and interior structure. Those instruments might be able to detect electromagnetic signatures from 3I Atlas or any objects it deploys, though they weren't designed for that purpose and might lack the sensitivity or pointing capability needed. The European Space Agency's JUICE mission, launched in 2023 and currently en route to Jupiter, won't arrive until 2031. No, too late to observe 3I Atlas directly. But there are other assets. Ground-based radio telescopes could search for emissions at frequencies that might indicate active electronic systems. Optical telescopes with wide-field capabilities could monitor the region around 3I Atlas for any objects that separate from the main body. Amateur astronomers, who've already proven instrumental in documenting the tail structures, could continue their observation campaigns and might spot anomalies that professional surveys miss. The coordination of all these observations will be crucial. Unlike most astronomical phenomena, which persist long enough that multiple independent observations can be scheduled at leisure, any deployment event from 3I Atlas would likely be brief, perhaps lasting hours or days rather than weeks. If something happens and only one facility is watching, the detection might be dismissed as instrument error or contamination. But if multiple independent observers see the same thing, the credibility increases enormously. That's why there's been effort to organise coordinated observation campaigns, time windows when as many telescopes as possible are directed at 3I Atlas, providing redundancy and cross-validation. The March flyby will be such a moment, an all-hands-on-deck effort to document whatever occurs with as much detail and reliability as possible. The data from that campaign, regardless of what it shows, will be archived and made available to researchers worldwide, ensuring that future analysis can revisit the observations as techniques improve or as theoretical understanding develops. And then there's the question of what we do if the evidence becomes compelling that 3I Atlas is indeed artificial. Does it change humanity's priorities? Does it shift resources towards SETI research and interstellar studies? Does it accelerate our own development of interstellar travel capabilities, driven by the knowledge that it's possible because someone else has already done it? Or does it trigger more defensive reactions, concerns about potential threats from civilizations whose capabilities far exceed our own? The policy discussions around these questions have already begun in certain circles. Quiet conversations in government science advisory committees and long-range planning groups exploring scenarios and considering responses. There's no consensus yet, partly because the scenarios themselves remain speculative, but the mere fact that such discussions are happening indicates how seriously at least some decision-makers are taking the possibility. The scientific community will continue its work regardless of policy responses, continuing to observe, measure, analyze, and debate as new data arrives. That's what science does. It follows evidence wherever it leads, even when the destination is uncomfortable or uncertain. The question of whether 3i Atlas is artificial will be answered eventually, either through accumulating evidence that makes one interpretation overwhelmingly more plausible than alternatives, or through direct observation that removes ambiguity entirely. We might get that answer in December when high-resolution instruments capture details that current observations can't resolve. We might get it in March when the Jupiter flyby either confirms or refutes the Hill radius coincidence. Or we might have to live with uncertainty for longer, waiting for some future encounter or technological development that finally provides the clarity we seek. But the question has been raised, the possibility has been articulated, and regardless of how it resolves, the mere fact that we're seriously considering whether an interstellar visitor might be artificial marks a transition point in how humanity thinks about its place in the cosmos and what we might encounter as we continue reaching outward toward the stars. The question has been raised, the possibility has been articulated, and regardless of how it resolves, the mere fact that we're seriously considering whether an interstellar visitor might be artificial marks a transition point in how humanity thinks about its place in the cosmos and what we might encounter as we continue reaching outward toward the stars. But while that philosophical transition unfolds in academic papers and public discourse, the immediate reality is more prosaic and more urgent. We have an object moving through our solar system right now, exhibiting behaviors that challenge explanation, and we have a rapidly closing window of opportunity to gather the data that might answer the fundamental question of what it actually is. The December observations represent our best chance, possibly our only chance, to resolve the ambiguities before 3i Atlas recedes beyond the reach of our most powerful instruments and becomes just another faint point of light disappearing into the cosmic background. The observation campaign being organised for mid-December involves coordination across multiple institutions and countries, a level of international cooperation that's impressive even by the standards of modern astronomy, where collaboration has become routine. The Hubble Space Telescope has dedicated observation time, multiple orbits allocated specifically for imaging 3i Atlas at maximum resolution. Hubble's aging cameras can't match the infrared sensitivity of newer instruments, but in visible wavelengths it still delivers exceptional image quality, and the archive of Hubble observations stretching back decades provides a baseline for comparison that helps identify changes and evolution in the object's appearance. The James Webb Space Telescope, humanity's most powerful space observatory, will point its infrared instruments at 3i Atlas during the closest approach window. Webb's capability to see through dust and gas makes it ideal for penetrating the coma and imaging the nucleus directly, potentially revealing surface features or structures that optical wavelengths can't resolve. And Webb's spectroscopic instruments will analyze the composition of the outgassing with unprecedented precision, measuring not just what elements and molecules are present, but also their velocities, temperatures, and spatial distributions. Ground-based observatories are also mobilizing. The Very Large Telescope in Chile, with its array of 8-meter mirrors and advanced adaptive optics that compensate for atmospheric turbulence, can achieve resolution rivaling space telescopes for bright objects. The Keck Observatory in Hawaii, with similar capabilities, provides an independent platform for verification and complementary observations. Radio telescopes including the Very Large Array in New Mexico and the Atacama Large Millimeter Array in Chile will search for electromagnetic emissions at frequencies that might indicate active systems or organized energy processes. And dozens of smaller facilities, university observatories and dedicated amateur installations will contribute their observations, creating a distributed network that ensures continuous coverage even if any single instrument experiences technical issues or weather delays. The sheer scale of the coordinated effort reflects both the scientific interest in 3i Atlas and the recognition that this might be a unique opportunity that won't repeat itself in our lifetimes. What exactly are these instruments looking for? The checklist of observational targets is extensive and carefully prioritized. First, high-resolution imaging of the nucleus itself, measuring its size, shape, and surface features with as much detail as the distance allows. If the nucleus is spherical or ellipsoidal, that's consistent with natural formation through accretion and gravitational collapse. But if it shows geometric features, straight edges, or flat surfaces or regular patterns, that would be difficult to explain naturally and would strengthen the artificial hypothesis. Second, detailed mapping of the outgassing jets, measuring their positions on the nucleus, their directions, their strengths, and how all these parameters change over time. Natural jets should correlate with solar heating, appearing on the sun-facing side and varying in intensity as different regions rotate into and out of sunlight. If the jets don't follow those patterns, if they appear in unexpected locations or maintain constant intensity regardless of solar angle, that suggests something other than simple thermal sublimation is driving the activity. Third, spectroscopic velocity measurements of the ejected material, the crucial test that might distinguish between natural outgassing and active propulsion. The spectrographs will measure Doppler shifts in emission lines from gas in the coma, determining how fast that gas is moving away from the nucleus. If the speeds cluster around a few hundred meters per second, consistent with thermal velocities for sublimating ice at the temperatures expected from solar heating, then natural processes can explain the observations. But if the velocities are higher, approaching or exceeding 1 kilometer per second, then you need energy input beyond thermal, something that's actively accelerating the gas to higher speeds. Fourth, searches for electromagnetic emissions beyond the visible spectrum, radio waves or microwaves or infrared radiation that might indicate active electronic systems or energy generation beyond what solar heating alone would produce. The previous detection of electromagnetic pulses from the core and the radio transmission during perihelion suggest that such emissions exist, but the December observations will search for them with greater sensitivity and broader frequency coverage, potentially revealing structure or modulation that earlier observations missed. Fifth, and this is more speculative but still worth attempting, searches for discrete objects in the vicinity of 3I Atlas, smaller bodies that might have been deployed from the main nucleus, or that might be accompanying it in formation. The deployment scenario predicts that if 3I Atlas is artificial, it might release smaller probes or instruments as it passes through regions of interest. The December observations won't be looking at the Jupiter Hill radius where such deployment might occur during the March flyby, but there's still value in checking whether any objects have already been released during the inner solar system passage. Finding even one such object would transform the entire investigation, providing a target for focused study, and potentially one that's more accessible or less ambiguous than the parent body. Sixth, monitoring for any changes in the rotation rate or axis orientation that might indicate active attitude control, maneuvering to point instruments or antennas in specific directions. Natural rotation tends to be stable over short timescales, changing only gradually due to outgassing torques or tidal effects. Active control would show up as sudden changes that don't correlate with expected physical processes. The timeline for these observations is compressed, everything happening during a window of just a few days around December 19th, when 3I Atlas reaches its minimum distance from Earth. Before and after that peak, observations continue but with lower priority and reduced resolution as the geometry becomes less favourable. The data will flow in continuously, raw images and spectra transmitted from telescopes to processing centres, where specialised software calibrates the measurements, removes instrumental artefacts, and formats the data for analysis. The initial assessments will happen quickly, within hours of the observations, as researchers examine the images and spectra looking for obvious anomalies or confirmations. But detailed analysis will take longer, weeks or months, as teams apply sophisticated techniques to extract every bit of information from the data, comparing measurements across different instruments, testing various physical models to see which ones fit the observations, publishing preliminary results, and then revised interpretations as understanding develops. There's an interesting psychological dynamic at work in the research community as this observation campaign approaches. Everyone wants to be the one who makes the crucial discovery, who captures the image or spectrum that definitively answers the question of what 3I Atlas is, that's natural, even healthy. Competition drives people to work harder, to be more creative in their analysis approaches, to double-check results and eliminate errors. But there's also awareness that the question is bigger than any individual career or reputation. that what matters is getting the right answer rather than getting credit. That tension between competition and cooperation, between individual ambition and collective goal, has always characterized science, but it's particularly acute when the stakes are as high as they are here. Confirming artificial origin would be career-defining, the kind of discovery that gets you into history books and ensures your name is remembered long after you're gone. But getting it wrong, announcing artificial origin prematurely based on ambiguous data, and then having to retract when better observations show natural explanations, that would be career-ending. So there's enormous pressure to be both bold enough to recognize significance when it appears, and cautious enough not to over-interpret noise as signal. The amateur astronomy community approaches this differently. For them, there's less career pressure, but more pure enthusiasm, the joy of participation in something meaningful, regardless of what credit they receive. The images captured by amateur observers in late November, showing the tail structures with clarity comparable to professional instruments, demonstrate that you don't need billion-dollar facilities to contribute to cutting-edge research. A skilled observer with modest equipment and dedication can capture data that's scientifically valuable, and in some cases can see things that professionals miss because they're focused on different targets or constrained by institutional priorities. There's been discussion about establishing a citizen science network specifically for monitoring 3i Atlas, coordinating amateur observations to provide continuous coverage that complements the scheduled professional campaigns. Such networks have proven valuable in other contexts, particularly for transient phenomena that require rapid response or continuous monitoring that's impractical for professional facilities. The technology exists, communication platforms and data sharing systems that allow distributed observers to coordinate their efforts and pool their results. What's needed is organization and leadership to channel the enthusiasm into systematic observation programs. As December approaches, there's also increased attention from media and public, not yet at the level where this becomes a mainstream news story, but growing awareness in science-focused communities and among people who follow space exploration. The challenge for communicating about 3i Atlas is managing expectations while conveying genuine excitement about what's being observed. Overhyping the story, promising definitive answers or claiming that artificial origin is certain would be irresponsible and would set up disappointment when the observations inevitably prove more ambiguous than simplified narratives suggest. But downplaying the significance, treating this as just another astronomical curiosity, without acknowledging the profound implications if the artificial hypothesis proves correct, that would be equally dishonest. The honest message is that we don't know yet, that the observations so far are intriguing and anomalous but not conclusive, and that the December data might provide clarity or might deepen the mystery depending on what they reveal. That's a nuanced message, harder to communicate than binary alternatives, but it's the truth. There have been some attempts by fringe media outlets to sensationalize the story. Headlines claiming NASA confirms alien spacecraft, or interstellar probe approaching Earth, that bear little relationship to what professional astronomers are actually saying. These distortions are frustrating but predictable. The boundary between legitimate scientific uncertainty and conspiracy theorizing is permeable, and anytime mainstream science acknowledges that something unusual is happening, there are always voices ready to interpret that acknowledgement as confirmation of whatever alternative narrative they're promoting. The responsible approach is to ignore the noise and focus on the signal, to continue doing rigorous science and communicating findings honestly while recognizing that you can't control how others will interpret or misrepresent those findings. Over time, data wins arguments. If 3i Atlas is natural, accumulating evidence will make that clear and the sensational claims will fade. If it's artificial, the evidence will build to the point where even skeptics have to acknowledge it. Either way, the process works if we trust it and give it time. Let's talk about what happens if the December observations don't resolve the question, if the data is detailed enough to rule out some explanations, but not definitive enough to confirm others. That's actually the most likely outcome. Science rarely delivers clean yes or no answers to complex questions. More often, observations narrow the range of possibilities, eliminate some hypotheses while leaving others viable, and set up the next round of observations that will further refine understanding. If December shows that the nucleus has unusual geometry, but not obviously artificial features, that the outgassing velocities are somewhat higher than purely thermal, but not unambiguously indicative of propulsion, that electromagnetic emissions exist but with structure that could be either natural or designed, then we're left in the same position of intriguing ambiguity we're in now, just with better data and tighter constraints. In that scenario, the March Jupiter flyby becomes even more crucial because it might provide the discriminating observations that December couldn't. The Jupiter encounter offers unique opportunities that Earth-based observations can't match. First, there's the Hill radius question, the statistical improbability that will either be confirmed or refuted by direct measurement of the flyby distance. If 3i Atlas passes inside Jupiter's gravitational dominance zone, that's a data point that demands explanation because the coincidence becomes too precise to attribute to chance. Second, there's the possibility of observing deployment events if they occur, changes in the object's appearance or trajectory or emissions that might indicate release of smaller components. Third, there's the opportunity for spacecraft observations from Juno or potentially other assets in the Jovian system, providing viewing angles and measurement capabilities that Earth-based instruments can't achieve. And fourth, there's the simple fact that Jupiter encounter represents the object's most dynamically interesting moment during its solar system passage, the point where gravitational forces are complex and where any active systems on 3i Atlas might need to respond to changing conditions. If something is going to happen, something visible and unambiguous, the Jupiter flyby is the most likely time. But there's also risk in placing too much emphasis on the March encounter, in building up expectations that might not be met. If 3i Atlas is natural, it will pass Jupiter without incident, following a trajectory determined purely by gravity and perhaps modified slightly by continued outgassing. There won't be deployment events or anomalous maneuvers or dramatic revelations. It will be, from an observational standpoint, anticlimactic. And if 3i Atlas is artificial but operating on logic we don't understand, it might pass through the Jupiter system without doing anything we'd recognize as significant. The deployment might have already happened, smaller objects released during the Perihelion passage when we weren't watching carefully enough. Or the deployment might happen later, farther out in the solar system where we won't see it. Or there might not be any deployment at all because this particular probe's mission doesn't include that phase. Attributing intention and purpose to something we don't understand is inherently speculative, and betting on specific predictions about what an alien artifact would or wouldn't do is a good way to be wrong. The more robust approach is to observe without strong preconceptions, to measure what's actually there rather than what we expect or hope to find, and to let the data shape conclusions rather than forcing data to fit predetermined narratives. That's harder than it sounds because humans are pattern-matching machines, evolutionarily optimized to see meaningful structure even in randomness, to construct stories that make sense of observation even when observations don't yet have enough detail to support definitive stories. The discipline required to say, "I don't know," and mean it, to resist the temptation to fill gaps in knowledge with speculation presented as fact, that's one of science's core values but also one of its hardest practices. It's especially hard when the question is as compelling as this one, when the alternative interpretations have such different implications that the desire to know which is correct becomes almost overwhelming. There's a scenario that doesn't get discussed much but is worth considering. What if 3i Atlas is neither purely natural nor purely artificial but something in between or outside those categories entirely? What if it's a natural object that's been modified by intelligence, a comet that was found and repurposed rather than built from scratch? What if it's an artificial object that's been operating for so long that natural processes have substantially altered its appearance, coating it in ice secreted during passage through molecular clouds, eroding its surface through micrometeorite impacts, changing its properties through cosmic ray bombardment until it looks almost natural? What if it's something biological, an organism or colony of organisms that evolved in space and that exhibits organized behavior without being technological in any sense we'd recognize? These possibilities sound exotic, and they probably are less likely than either the simple natural or simple artificial alternatives, but they're not impossible. The universe has had billions of years and vast volumes of space to experiment with different forms of organization and complexity. Our categories, natural versus artificial, living versus non-living, designed versus accidental, these are human constructs that might not map cleanly onto reality, especially reality that evolved under conditions vastly different from Earth's. Keeping an open mind about such possibilities while still maintaining evidentiary standards is the balance science aims for. You don't dismiss ideas just because they're strange, but you don't accept them without evidence either. You remain willing to be surprised, to discover that the universe works in ways you didn't anticipate, while also remaining skeptical of claims that aren't supported by solid data. It's a dance between imagination and rigor, between creative hypothesis generation and careful hypothesis testing. And it's the dance that will continue through the December observations and beyond as we work toward understanding what 3i Atlas actually represents. The answer might be simple, a weird comet that's teaching us about exotic processes we hadn't encountered before. Or it might be complex, something that challenges our categories and forces us to develop new frameworks for thinking about what's possible in the cosmos. Either way, the process of finding out is valuable in itself, regardless of where it leads. Let's return once more to the specifics of what we're observing and why it matters so much. The anti-tail, those cosmic headlights pointing sunward with such unexpected persistence, represents a physics problem that doesn't have a satisfying natural solution yet. We've explored the energetics, the requirement for either extremely high velocity or extremely high mass density to push material against the solar wind. But there's another aspect worth examining, the question of what the anti-tail is actually made of. Spectroscopic observations show that it contains dust and gas, similar in composition to the main tail, but possibly with different grain size distributions. If the anti-tail material consists of unusually large particles, chunks of ice or dust grains measured in millimeters or centimeters, rather than the micron-scale grains typical of cometary tails, that could explain some of its properties. Large particles have more momentum for a given volume and are less affected by radiation pressure from sunlight, allowing them to maintain trajectories that smaller particles couldn't follow. But this explanation creates its own problems. How do you eject large particles from a comet nucleus? Thermal sublimation typically releases individual molecules or small clusters, not macroscopic chunks. You'd need something more violent, explosive outbursts driven by pressure build-up beneath the surface, or perhaps fracturing of the ice causing mechanical breakup that throws fragments into space. Such processes can happen, and we've observed them on other comets, but they're usually transient events, brief episodes of enhanced activity rather than sustained release over weeks and months. For 3i Atlas to maintain the anti-tail through continuous or frequently repeated explosive events would require internal structural composition very different from typical comets. Maybe there are large voids inside the nucleus, pockets where sublimating gas accumulates until pressure exceeds the strength of the overlying ice and causes breakout. Maybe the ice has unusual mechanical properties, brittleness, or layering that promotes fracturing. Maybe the rotation and thermal cycling create stress patterns that repeatedly crack the surface and eject material. All of these are possible in principle, but each requires fairly specific conditions. The alternative, that the anti-tail represents something other than natural ice ejection, becomes more plausible the more difficulties you encounter trying to explain it naturally. If the material is being actively expelled rather than passively released by sublimation, if there's a mechanism generating directed thrust that launches particles sunward at high velocity, then the observations make sense. You don't need catastrophic mass loss or exotic grain properties or unlikely geometric coincidences. You just need a system capable of accelerating material and pointing it in a specific direction. For a technological object, that's straightforward, routine even. Rockets do it. Ion drives do it. Any propulsion system does it by definition. The anti-tail becomes not a mysterious anomaly, but simply exhaust, the visible signature of propulsion systems operating to adjust trajectory or maintain orientation. And if that's the case, then the persistence and scale of the anti-tail tells you about the capabilities of those systems, the thrust levels they can generate and the duration they can sustain operation, information that might be valuable for understanding what kind of technology we're dealing with. The question of why a probe would have its exhaust pointing toward the sun rather than in some other direction leads to interesting speculative possibilities. If you're trying to slow down, to shed velocity as you fall toward the inner solar system, you'd want to thrust in the direction opposite to your motion, creating drag that reduces your speed. For an object on an inbound trajectory, opposite to motion means generally sunward, because you're moving from the outer solar system toward the sun. So a continuous sunward pointing exhaust could represent a braking maneuver, an attempt to reduce velocity to achieve a specific trajectory, or to prepare for orbital insertion around the sun or a planet. Alternatively, if you're trying to maintain a specific orientation, to keep solar panels facing the sun for power generation, or to keep instruments pointed in particular directions, you might need continuous low-level thrust to counteract rotation or to resist torques from asymmetric solar radiation pressure. That thrust might be directed in whatever direction is needed for attitude control, which could sometimes be sunward. These scenarios are speculative, built on assumptions about what an artificial probe might be trying to accomplish and how it might accomplish those goals. But they're not arbitrary speculation. They're based on engineering logic and orbital mechanics principles that apply regardless of who or what built the system. Any object trying to operate in a solar system faces the same physical constraints, the same gravitational fields and radiation pressures and thermal environments. The solutions to those constraints, the strategies for navigation and power and thermal management, should follow similar logic whether the object was designed by humans or by intelligence from elsewhere. So when we speculate about what 3i Atlas might be doing if it's artificial, we're not inventing from nothing. We're applying knowledge we've gained from our own space exploration efforts and extrapolating to higher technology levels and longer timescales. That doesn't guarantee our speculations are correct, but it grounds them in reality rather than pure imagination. The December observations will test some of these ideas. If the antitail continues to evolve, if it changes in strength or direction or structure in ways that correlate with changing distance from the Sun or changing orbital geometry, that tells us something about what drives it. If it shuts off suddenly, that suggests active control rather than continuous passive release. If it persists unchanged despite the decreasing solar heating, as 3i Atlas moves farther from the Sun, that's another indicator that thermal processes aren't the primary driver. The detailed spectroscopy might reveal velocity gradients or chemical compositions that further constrain possibilities. Every measurement narrows the solution space, eliminating hypotheses that don't match data and strengthening those that do. Slowly, methodically, the picture clarifies. Maybe not all the way to certainty, not in December or even in March, but incrementally toward better understanding. There's a parallel investigation happening alongside the observational campaign, though it receives less public attention. Theorists are developing detailed models of what an interstellar probe might look like based on known physics and plausible technology. These studies start with constraints. The object must be able to survive millions of years in interstellar space, must be able to navigate and maneuver using available energy sources, must be able to gather and transmit information over interstellar distances, must be autonomous since real-time control across light years isn't feasible. From those constraints, you can derive requirements for materials, for energy systems, for computing architecture, for communications protocols. And then you can ask whether the observations of 3i Atlas are consistent with meeting those requirements. The answer appears to be yes. The exotic isotopes could provide long-lived radioactive power sources. The core density matches what you'd expect from compact energy storage and shielding. The electromagnetic emissions match what would be necessary for active systems. The size is about right for a probe that's substantial enough to carry scientific instruments, but small enough to be practical for interstellar launch. These theoretical models don't prove 3i Atlas is artificial, but they establish that artificial is plausible, that the observations are consistent with engineering design if such design exists. That's different from proving design exists, but it's also different from dismissing the possibility as incompatible with known physics. The models also make predictions about what additional observations should reveal if the artifact hypothesis is correct. For instance, they predict that the electromagnetic emission should show structure related to power management, periodic variations as systems cycle on and off to conserve energy. They predict that any propulsion system would likely use the most efficient available technology, probably electric propulsion with exhaust velocities measured in tens of kilometers per second. They predict that materials exposed to millions of years of cosmic ray bombardment would show specific isotopic signatures from nuclear reactions induced by high-energy particles. These predictions can be tested against observations, providing a way to evaluate whether the theoretical models capture the reality of 3i Atlas, or whether they're just elaborate constructions that happen to fit some data, but miss the essential nature of the object. The sociology of how the scientific community handles this investigation is itself interesting to observe. There's a generational divide, with younger researchers generally more willing to consider the artificial hypothesis seriously, while older, more established scientists tend toward conservative interpretations. That's a pattern you see in many scientific controversies. Younger researchers have less invested in existing paradigms and more to gain from revolutionary discoveries. Older researchers have spent careers building expertise within current frameworks and are naturally more protective of those frameworks. Neither position is inherently wrong. The conservatism of experienced researchers prevents the field from chasing every anomaly down rabbit holes that lead nowhere. The openness of younger researchers ensures that genuinely novel phenomena get investigated rather than dismissed. The tension between these positions drives progress, each side pushing the other toward more rigorous argumentation and better evidence. There's also a geographical component. Researchers in some countries seem more comfortable publicly discussing the possibility of artificial origin than those in others, possibly reflecting different cultural attitudes towards speculative thinking or different institutional pressures around maintaining scientific credibility. The American scientific establishment has been particularly cautious, with NASA and major universities carefully hedging their statements and emphasizing that no definitive conclusions can be drawn yet. European researchers seem slightly more willing to engage with the artificial hypothesis in public forums, though still maintaining appropriate skepticism. And researchers in some Asian countries have been quite open about considering artificial origin as a serious possibility deserving investigation. These differences don't reflect different data. Everyone has access to the same observations, but rather different cultural contexts for how to think about and communicate about uncertain, high-stakes questions. The question of what happens to the broader SETI field, the search for extraterrestrial intelligence, if 3i Atlas proves to be artificial, is worth considering. SETI has traditionally focused on detecting radio signals from distant civilizations, listening for broadcasts or communications that would indicate technological intelligence exists elsewhere. The field has struggled with funding and credibility because decades of searching have produced no confirmed detections, leading some to question whether the approach is viable. But if 3i Atlas is artificial, it represents a completely different mode of contact, not a remote signal, but a physical presence. Not communication across light years, but an artifact in our own solar system. That would validate SETI's fundamental premise that technological intelligence exists beyond Earth, while also suggesting that detection might come through methods SETI hasn't traditionally emphasized, through careful study of objects passing through our neighborhood rather than through radio astronomy. There's been discussion about whether SETI should expand its scope to include searches for artifacts, what's sometimes called artifact SETI or archaeological SETI. The idea is that advanced civilizations might leave traces of their presence that persist long after they've gone. Ruins on airless moons, waste heat from megastructures, or probes like 3i Atlas wandering the galaxy. These artifacts might be easier to detect than faint radio signals, especially if they're nearby in our own solar system. The Breakthrough Listen project, one of the most ambitious current SETI efforts, has already begun incorporating searches for anomalous objects and unexplained phenomena in solar system observations. If 3i Atlas proves to be artificial, that emphasis will increase dramatically, with renewed searches through existing databases looking for other candidates and new observation programs designed specifically to find and characterize unusual objects that might have artificial origins. The public reaction to confirmation of artificial origin is difficult to predict. Science fiction and popular culture have prepared people for the idea that alien intelligence exists. But there's a difference between abstract possibility and concrete confirmation. Some people would react with excitement and wonder, thrilled to have the cosmic loneliness broken and eager to learn what the artifact might teach us. Others would react with fear, worried about potential threats from civilizations whose capabilities exceed ours by unknown margins. Still others would react with religious or philosophical confusion, struggling to integrate the reality of alien intelligence with belief systems that don't easily accommodate it. And many would simply be indifferent, seeing it as an interesting curiosity, but not something that changes their daily lives or immediate concerns. The actual social impact would depend heavily on how the discovery was communicated, what narratives emerged around it, and what, if any, practical implications it had for human society. One scenario that's been considered is that confirmation of artificial origin might unify humanity in unprecedented ways, providing a shared focus that transcends national and cultural divisions. The idea is that facing evidence of intelligence beyond Earth would make our species-level commonalities more salient than our intra-species differences, promoting cooperation and reducing conflict. This is a hopeful scenario, and there are historical examples of external events that temporarily unified competing factions, but it's probably overly optimistic. Human divisions are deep-rooted and complex, and it's unlikely that even confirming alien technology would magically dissolve them. More realistic is that 3i Atlas would become another topic around which existing divisions play out, with different groups interpreting the discovery through their existing ideological lenses and reaching different conclusions about what it means and how to respond. The alternative scenario, that confirmation of artificial origin, leads to increased conflict as nations and groups compete for access to the technology or argue about how to respond, is darker but also plausible. If 3i Atlas contains technology far beyond our current capabilities, the potential economic and military advantages from understanding and potentially replicating that technology would be enormous. There would be intense pressure to capture the object if possible, to prevent other nations from accessing it, to extract whatever value can be extracted before the opportunity disappears. International cooperation might break down under those pressures, replaced by competition and secrecy. This scenario assumes that 3i Atlas is accessible in ways that make capture and study feasible, which is far from certain given its trajectory and speed, but the mere possibility might be enough to trigger competitive responses even if actual capture proves impossible. The legal questions around an artificial interstellar object are fascinatingly complex and completely unresolved. Current space law, embodied in the Outer Space Treaty and related agreements, deals primarily with activities by nation-states and doesn't clearly address how to handle artifacts from non-terrestrial intelligence. Who owns 3i Atlas if it's artificial? Who has the right to study it or potentially retrieve samples? Who decides what information should be shared publicly versus kept confidential for security reasons? These questions don't have clear answers in existing legal frameworks. The Outer Space Treaty declares that celestial bodies can't be claimed by any nation and should be explored for the benefit of all humanity, which might suggest that 3i Atlas should be studied cooperatively and findings shared openly. But the treaty was written with natural celestial bodies in mind, not artifacts that might contain valuable technology, and it's unclear whether its provisions would apply or how they'd be interpreted in this unprecedented situation. Practical reality is that whoever has the capability to reach and study 3i Atlas will likely do so regardless of unclear legal status. If a mission to intercept the object is launched, it will almost certainly be a national effort or maybe an international collaboration, and whoever funds and conducts that mission will have de facto control over the resulting data and any samples returned. The legal niceties can be worked out afterward. This might seem cynical, but it's realistic about how space exploration has generally worked, where capability determines outcomes more than legal frameworks. The hope is that enough international cooperation exists that major findings would be shared widely, but there's no guarantee of that, especially if military or economic interests suggest that secrecy provides advantages. As we approach the December observations, there's a palpable sense of anticipation in the communities following this story. Not the breathless excitement of popular media looking for sensational headlines, but the quieter, deeper anticipation of people who understand the implications and are waiting to see what rigorous observation will reveal. For astronomers, it's the feeling you get before a major telescope observation or a spacecraft encounter, the knowledge that you're about to gather data that might answer questions you've been thinking about for months or years. For theorists, it's the anticipation of having models tested against reality, of seeing whether predictions prove accurate or whether nature surprises you once again. For the broader public who've become aware of 3i Atlas, it's the hope that we might be living through a historically significant moment, that the question of whether we're alone in the universe might move from philosophical speculation to empirical knowledge. The timeline is set. December 19th marks closest approach and the peak of observation intensity. The data will flow in over the following days and weeks as different instruments complete their observations and transmit results. Initial analysis will happen quickly, preliminary assessments within hours or days, but detailed studies will take longer, months of careful work examining every detail, cross-checking measurements, testing interpretations against alternatives. Papers will be written and submitted to journals, where peer review will subject claims to scrutiny before publication. Conferences will be held where researchers present findings and debate implications, and gradually a consensus will emerge. or it won't if the data remains too ambiguous to support definitive conclusions. That's how science works, messily and slowly but ultimately reliably, building understanding through accumulated evidence and rigorous testing of ideas. And then, assuming December doesn't provide complete answers, we wait for March. The Jupiter flyby will be different in character from the Earth observations, less about detailed imaging and more about trajectory and dynamics. The key question will be whether 3I Atlas passes inside Jupiter's Hill radius, whether that statistical improbability proves real or evaporates as refined calculations push the flyby distance outside the boundary. If it passes inside, the probability calculations that made it seem so unlikely become real, and we have to confront what that means. If it passes outside, even marginally, then maybe it's coincidence after all, or maybe the JPL models were right and the revised trajectory is accurate. But either way, the March encounter represents a milestone, a point where one significant prediction is tested against reality. The possibility of deployment during the Jupiter encounter adds another layer of anticipation. If smaller objects separate from 3I Atlas, if anything changes in its emissions or appearance or trajectory in ways that suggest intentional action, that would be difficult to explain naturally. We'll be watching for exactly those signs, looking for any indication that this object is doing more than just following gravitational trajectories and responding to solar heating. The instruments will record everything, capturing data at high cadence to ensure that brief events aren't missed, and teams will be standing by to analyze incoming data in real time, ready to adjust observation plans if something unexpected appears, ready to trigger follow-up measurements if initial detections need confirmation. But there's also the very real possibility that March comes and goes without any dramatic revelations, that 3I Atlas passes Jupiter exactly as gravitational models predict, that nothing separates or changes or behaves in obviously artificial ways, and that we're left with the same ambiguity we have now, just with more data constraining the possibilities. That outcome would be disappointing to those hoping for definitive answers, but it wouldn't be the end of the investigation. Science rarely works through sudden revelations that settle questions completely. More often, understanding builds incrementally through accumulating observations that gradually favour one interpretation over others. Even if December and March don't provide smoking gun evidence, they'll provide information that shapes how we think about 3I Atlas and how we approach future observations. And there will be future observations, at least for a while. 3I Atlas will remain observable through much of 2026 as it moves outward past Jupiter and toward the outer solar system. The object will get fainter as distance increases and solar heating decreases, eventually crossing below the detection threshold of all but the largest telescopes. But until that point, monitoring will continue. Periodic check-ins to see if anything changes, if late-stage activity appears, if the trajectory shows any additional anomalies. The long tail of observation, the months and years after the peak events of December and March, might reveal patterns or behaviours that aren't apparent in short-term studies. Patience is a virtue in astronomy, where objects evolve on timescales of months or years, and where understanding sometimes requires watching for longer than you'd prefer. There's also the possibility, remote but worth mentioning, that 3I Atlas isn't the end of this story but the beginning. If it's artificial, then presumably other such objects exist. Other probes from the same civilization or from different civilizations pursuing similar exploration strategies. Our improved detection capabilities mean we're finding more interstellar objects than we did even a few years ago. Before Oumuamua in 2017, we'd never confirmed a single interstellar visitor. Now we have 3 confirmed and likely many more in the data waiting to be recognized. As survey telescopes improve and as we get better at distinguishing interstellar trajectories from ordinary solar system orbits, the detection rate will increase. We might find several interstellar objects per year within the next decade, and with each new detection, we get another opportunity to test the artificial hypothesis, to see whether the anomalies we've seen in 3I Atlas are unique to this one object, or represent a broader pattern. If multiple interstellar objects show similar characteristics, electromagnetic emissions and controlled behaviour and trajectory optimization that would strengthen the case for artificial origin far more than any single object could. One anomalous object might be a fluke, a weird natural phenomenon we don't understand yet, but multiple objects showing the same patterns would be harder to dismiss as coincidence. Conversely, if future interstellar visitors are clearly natural, typical comets or asteroids with no hint of the features that make 3I Atlas unusual, that would suggest 3i Atlas is either a unique natural phenomenon or a unique artificial one, an isolated probe rather than part of a population. Either way, the broader context matters. 3i Atlas shouldn't be evaluated in isolation but as part of the emerging sample of interstellar objects we're beginning to catalogue. The field of interstellar object studies is in its infancy. We're still developing the tools and techniques needed to characterise these visitors effectively. We're still building the theoretical frameworks for understanding what's possible and what different observations imply, and we're still learning to distinguish between genuinely anomalous properties that require new physics or new hypotheses and apparent anomalies that result from limited data or observational biases. 3i Atlas is teaching us how to do this work, forcing us to develop methods and confront questions we didn't have to address when studying ordinary solar system objects. Even if it turns out to be entirely natural, even if every anomaly gets explained by exotic but understood physics, the investigation will have advanced the field in valuable ways. But if it's not natural, if the evidence continues to accumulate in ways that make the artificial hypothesis increasingly compelling, then we're in uncharted territory, not just scientifically, but culturally and philosophically. The confirmation that intelligence exists or existed beyond Earth would be one of those watershed moments that divides history into before and after. Before we knew, and after we knew. The world wouldn't change overnight. Daily life for most people would continue much as before, but the context for everything would shift. We'd know we're not alone, not the universe's only experiment in complexity and awareness. We'd know that the process that produced us, whatever combination of chemistry and physics and chance that led from simple molecules to living cells to thinking beings, that process has occurred elsewhere, maybe many elsewheres, maybe commonly throughout the galaxy. That knowledge changes things in subtle but profound ways. It changes how we think about our future. If others have survived long enough to develop interstellar capabilities, then survival must be possible, which means our current challenges and threats aren't inevitably fatal. It changes how we think about our significance. We're not cosmically unique or central, but we're part of a broader story, one thread among potentially many in the universe's exploration of what organisation and complexity can achieve. It changes how we think about exploration and discovery. We're not alone in looking outward and asking questions. Others have done it before us, and their artifacts or signals or presence might be detectable if we look carefully and think creatively about what to search for. And it changes how we think about our responsibilities. If intelligence is rare and precious and fragile, if most of the civilizations that develop technology fail to survive their own capabilities and destroy themselves before reaching the stars, then we have an obligation to be the exception, to solve the problems that threaten us, and to ensure that humanity becomes one of the success stories rather than another cautionary tale lost to history. The existence proof that at least one civilization succeeded in building something that endures across millions of years would be both inspiration and challenge, showing what's possible while also highlighting how far we still have to go. These are the thoughts that occupy the minds of those following 3i Atlas closely, the implications that make this more than just an astronomical curiosity. The object itself, whether it's comet or probe or something else entirely, is fascinating in its own right. But what it represents, the questions it forces us to ask about our place in the cosmos and what might exist beyond our small corner of space, those questions resonate at depths that pure science can't fully capture. We're not just measuring an object's position and composition. We're measuring ourselves against possibilities we've imagined but never confirmed, testing whether the universe we inhabit is one where intelligence emerges once or many times, where technological civilizations are commonplace or rare beyond measure. The data will decide. Not our hopes or fears, not our philosophical preferences or cultural narratives, but the data, the measurements made by instruments designed to capture photons and particles and convert them into numbers we can analyze. The spectra that tell us what elements and molecules are present and how fast they're moving. The images that show us shapes and structures and how they change over time. The trajectory calculations that tell us where the object came from and where it's going, and whether its path follows gravitational physics alone or shows evidence of additional forces. All of this reduces to numbers in databases, patterns in data that either fit models or don't, observations that either support hypotheses or contradict them. That's the beauty of science, the way it grounds speculation in measurement and replaces debate with evidence. And so we return to where we started, with an object moving through our solar system that challenges explanation and demands attention. The antitail streams sunward with persistent improbability. The electromagnetic core pulses with mysterious rhythm. The trajectory threads toward Jupiter with precision that stretches coincidence. The non-gravitational acceleration appears exactly when and where it would be most useful for changing course. The spectroscopic signatures suggest compositions and processes unlike anything we've seen before. Each observation adds to the picture, each measurement constrains the possibilities, each analysis brings us incrementally closer to understanding what 3i Atlas actually is. December will bring new data, potentially transformative data if the observations are as detailed as planned. March will test predictions and might reveal behaviours that current observations can only hint at. And beyond those milestones, the investigation continues as long as the object remains observable, and as long as questions remain unanswered. The story of 3i Atlas is still being written, each observation adding another paragraph, each analysis another interpretation, each debate among researchers another revision to the narrative. We don't know yet how the story ends, whether it concludes with natural explanation, or artificial confirmation, or continued ambiguity that persists until the object fades from view and we're left with incomplete answers. But we're watching it unfold in real time, witnessing the process of discovery as it happens, participating in the collective human effort to understand what's moving through our cosmic neighbourhood and what it means that it's here. That participation, that engagement with questions larger than ourselves, might be the real value regardless of what conclusions we eventually reach. Because in asking whether 3i Atlas is natural or artificial, we're really asking deeper questions about what's possible in the universe, what forms intelligence and technology might take, and whether the cosmos we inhabit is populated by other minds asking similar questions from their own corners of space and time. The answer is coming. The December observations will reveal what they reveal. The March flyby will show what it shows, and gradually, as data accumulates and understanding develops, we'll know. Or we won't, not completely, not with certainty, but we'll know more than we do now. We'll have better constraints on possibilities, and stronger reasons for favouring some interpretations over others. And that incremental progress, that slow movement from ignorance toward knowledge even if complete knowledge remains elusive, that's how humanity expands its understanding of the universe and its place within it. One observation at a time, one measurement at a time, one object at a time. And right now that object is 3i Atlas, mysterious visitor from the stars, carrying either exotic ice or ancient technology, or perhaps both, crossing our solar system while we watch and wonder and work to understand what we're actually seeing when we point our telescopes toward that peculiar point of light moving against the background stars with its impossible antitail and its unexplained emissions and its trajectory that seems just a little too precise to be entirely accidental. The truth is out there, literally out there, moving through space at 20 kilometers per second. And we're chasing it with everything we have, all our instruments and intelligence and determination, trying to catch it before it slips away into the darkness from which it came. The chase is on. The observations are planned, the analyses are ready, and soon, very soon, we'll have answers. Or at least we'll have better questions, which in science is often the next best thing.